Swayam Prabha. Digital India. Educated India.
Okay, welcome back everyone, and in this particular module we were discussing on an object which is moving in a resisting medium. So what we have is, suppose let us now simplify our problem at hand. Let me say that we have a rigid object, let's say rigid sphere, which is moving in a liquid. Even air is a liquid, right? So for a rigid sphere moving with constant velocity through an incompressible fluid, we have with radius a and speed v. Well, I should just say velocity v, because we are talking about general velocities, okay, with direction. And density, the density of the fluid is, let's say, rho, and the viscosity is mu of the fluid, right? So these are the various parameters in fluid dynamics. I'm not going to dive deeper into these parameters, but rather I would like to highlight some essential results. Almost all these results have been found by extensive research, and there are a lot of publications around this results in this field. So in the case, if we have when we have the object, if the sphere is moving, there are two results that I want to highlight. If the sphere is moving fast, then it turns out that the drag force in this case is analytically found out to be C times rho a square v square, where C is a constant which is roughly equal to 0.8. Notice that in the case of fast movement, the drag forces are depending on the square of the velocity, right? Now, based on this drag force, we also introduce a so-called concept of Reynolds number. So what is Reynolds number? Typically, Reynolds number is a dimensionless number representing the ratio of inertial to viscous forces. Okay, so Reynolds number is a dimensionless quantity. It's a dimensionless quantity which is R, which is given by rho times V times A divided by mu, where rho is the density of the fluid in which the object is moving, V is the velocity of the object, A is the size of the object, mu is the viscosity of the fluid in which it is moving. And sometimes we can also write the Reynolds number as follows. This is rho times A divided by mu by V, and this V is nothing but mu. I call this V as nu, which is my so-called kinematic viscosity, right? Sometimes people work with simple viscosities, sometimes people work with so-called kinematic viscosities, and these are the various formulas for Reynolds number based on either of the viscosities. Okay, so when we talk, so why have I introduced this parameter? Because typical way of measuring the speed of the system or how fast the system is moving depends on the value of the Reynolds number. So if the value is large, we expect the object to be moving fast. Notice that Reynolds number is directly proportional to the velocity of the object, right? It is directly proportional, which means faster the velocity, larger the Reynolds number, right? So when we have Reynolds number, let me abbreviate it with Re. If this goes to infinity, or very large, I would say. I should not write like this, but the better way of writing is, if Reynolds number is very large, then this formula for the drag holds. again, this is a research result. I don't want to dive deeper into the origin of these results, right? Typically, there are typical terminal velocity experiments which quote these results. Okay. Now, what happens when it is the other limit? That is when Reynolds number goes to 0 or we have a extremely slow velocity of the sphere. In that case, the drag result, this particular drag result doesn't hold and we have a new result. The result is the result says that when my Reynolds number r goes to 0, we have the drag result is 6 pi by r, sorry, the constant, and my drag comes out to be, well, I don't need this constant here. I'll directly give you the result. My drag is 6 pi a mu v, right? So my drag is 6 pi a mu v, and that is the case when the Reynolds number is 0, right? So now notice that in this case the drag directly depends only linearly on the velocity. So this is the linear law of resistance. Linear law of resistance, right? Linear law of resistance. So we have to identify what regime we are talking, and then only we have to plug in the appropriate formula for drag. Otherwise, we are going to get nonsensical results as shown in the next example. Okay, so let us look at one example. Let me call this example 4. So here we have a steel ball of radius 1 mm, which is falling vertically, right? A steel ball of radius 1 mm which is falling vertically with constant speed, in air. So it is falling vertically with constant speed in air. We have to find the speed of the ball, right? The speed of the ball in the medium. Okay, so the ball is moving in air, right? And the second, so that is part first, and the second part says is if the medium is castor oil, well, just to tell you a bit more, castor oil is a thicker medium compared to air. So if the medium is castor oil, then what would be the speed? What is the ball's speed? Okay. Now the intuition tells us in the presence of a thicker medium, the ball is going to travel slower. Let us see what the problem tells us. The solution tells us. So before that, I just want to highlight that the density of the steel, this is steel ball, the density of the steel ball is 7800 kg per meter cube. So this is something we will use. Okay. So what we have is, notice that if the ball is moving down, in a medium which is, let's say, air or fluid, any fluid, then the ball is being driven by its weight, right? But then the ball, when it is being driven by the weight of its own weight, it is also displacing the fluid, right? So when a ball is moving in a fluid, it is displacing the fluid. This is typical law of buoyancy. So if the ball is moving through a fluid, then it is equally displacing an equal amount of fluid, that is the same as the volume of the ball, right? So then we have to write the appropriate force balance for this ball moving in a fluid. So what we have is that it turns out that the force balance, okay, the force balance tells us the following, that we have the weight of the displaced fluid mg plus d, right? So if we have this is my weight of the displaced fluid, displaced, this is due to buoyancy, right? This is going to be m prime g, which is the weight of the ball, right? Weight of the ball. and this is my drag force on the ball. My drag force on the ball. So my drag force which I want to find is going to be G times m prime minus m, which is m prime is the mass of the ball, depends on the density of the steel, and m is the mass of the fluid in which it is moving, depends on the density of air, right? So from here I can directly write down. So suppose we are talking about a small ball, so I don't know which formula to use for the drag, but let us start using the formulas and let us see what answers are we going to get. So assuming slow motion, we can use the formula of the drag, which is this second formula which I have stated. So my drag comes out to be, so we see my drag is g times m prime minus m, and my drag comes out to be 6 pi a rho by nu, where rho is the density of the steel, and this is going to be, we are talking about masses, we have to change it into volumes. So this is going to be, these are all spheres, so these are 4 by 3, volume is 4 by 3 pi a cube times g times rho prime minus rho, right, where rho prime is the density of the steel and rho is the density of the fluid. From here I can find, so what do we get? See, this is my velocity v of the ball. We need to find the speed of the ball. So to find the speed of the ball, from this formula we get that v comes out to be 2a square g by 6, what else? I think we have missed a coefficient nu, which is this nu, this coefficient here. Okay, so let us keep it mu. So 2a square g by 9 mu times rho prime minus rho by minus 1. So after all these simplification, the velocity comes out to be this, and now we start plugging in the various values of steel and the air. So density of steel, density of air, and the viscosity of air, and the radius of the ball, and so on. After plugging in the various values, we get that v comes out to be roughly equal to 940 meters per second. That's a large velocity, right? And from here we get that the Reynolds number, that is when we plug in the formula in the Reynolds number, we get that this is roughly equal to 63,000. That's a huge value of Reynolds number for a small ball, a tiny ball falling through the air, right? Now let us see. So something, before I move ahead, we also have to find the speed in the castor oil. But before I move ahead, it seems something is off track here, right? You cannot expect a ball to travel with such high velocities and with such high Reynolds number. I think, and then this question that we have to ask ourselves is, where lies the problem? The problem lies in this assumption where we have assumed the drag is a linear law. So let us see what happens when we take a quadratic law for the drag, that is one for the higher velocity case, right? So when we take the quadratic law, suppose we take the quadratic law, we see that c times rho a square v square is 4 by 3 pi a cube rho prime minus rho times g, right? And once we plug in all the values, I am going to get that v is roughly equal to 19 meters per second. That is quite a manageable number, right? And from here we get the Reynolds number to be roughly 1250. So these values seems more believable compared to the values that we had found for the linear law case. So it turns out that in this particular case, the ball is following the quadratic drag law case. Now for the castor oil, the part B, castor oil, I'll just write down the density of the castor oil, and then the listeners can start plugging in the values. We see that the kinematic viscosity of the castor oil is the following: 1.04 into 10 to the power minus 3 meters square per second, And from here we see that if we use the quadratic, well, this time if we use the linear law, then we are going to get that V is roughly 1.5 centimeters per second, and the Reynolds number comes out to be 0.015. So the castor oil is quite a thick substance, and it significantly increases the drag of the particle on the particle and reduces its velocity. Okay. So what have we got here? So what have we got is the following. So what we have is, so that completes in terms of our description of the fluid mechanics of the particle in a resisting medium. So now let us look at some other examples of particle moving in a resisting medium. So example 5. So here is a body. Suppose now let us go back to our projectile example, right? So far we have done 1 or 2 examples in projectile where we throw the ball in the air. The only thing missing in those projectile example is the realistic assumption that the ball is being resisted by the air or being dragged down. So there is the friction or the air resistance is missing in those examples. So let us now introduce the case of air resistance on the ball moving upward. Okay. So again, the body, we have a body which is projected upward, body which is vertically projected upward, vertically upward with speed u in a medium that exerts a drag force, right? So we have minus mkv. Well, so k is the proportionality constant. We always know that the air resistance or the friction forces always depend on the velocity, and of course it depends on the size of the object in terms of its mass. So this is what the drag force is. We have to find the maximum height this time in the resisting medium, and we have to find the time of the time taken to reach that height, right? And we have to also find the so-called terminal speed. So this is a new concept in resisting medium. What is terminal speed? Terminal speed is the speed of the object when there is no net acceleration. That is, the object is moving as if it is moving with a steady velocity, right? So that is terminal speed. So let us now write down the equations of motion. We have mv dot is equal to minus mg. So that is for the equation of motion for the normal medium, minus mkv. So that is my terminal speed, right? And then we can see that the equation once we integrate. So we are going to integrate this system. We integrate with, let's say, initial condition v at t equal to 0 is u. Let's say at t equal to 0 velocity v is u, and then we have that t is, after integrating we can immediately find the time taken is 1 over k times log of g plus ku divided by g plus kv. Okay. So now we have to find, so we have already found what is the total time in terms of the velocity. We have to find the maximum height. So when is the maximum height? When the velocity v comes out to be 0. So by the way, this is both the same v, small v. So when we set v equal to 0, we will get the time taken to reach the maximum height, and then we integrate this equation once more to find the height, right? So what did I just said? So the max height is reached when v is equal to 0, right? The particle stops, And from here we see that tau is 1 over k times log of 1 plus ku by g. We have set v equal to 0, and this is my time taken to reach the maximum height, right? So again, if we look at this particular equation, let me call this expression as 1, and we find from 1, if we find v as a function of t, we are going to get that v as a function of t comes out to be the following: e to the power minus kt minus g over k 1 minus e to the power minus kt, right? And so this is the formula for velocity. We can quickly find the terminal velocity. The terminal velocity can be found in two ways. One way is that we set the net force to be 0, right? That there is no acceleration of the system. We set the net force is equal to 0, and from here we can immediately find the terminal velocity. That is, v terminal is going to be minus g over k, right? So that is the terminal velocity. The other way the terminal velocity can be found is, look at the velocity expression. So it turns out that when a long time has passed, right, the body is no longer under the action of force. That is, when enough time has passed, the body is eventually going to follow its motion with the terminal velocity, right? So the terminal velocity is when the time t goes to infinity. So when the time t goes to infinity, we plug it in this formula and we are going to get v is equal to minus g over k, which is what the terminal velocity is, right? Now the final thing that is left is we have to find the maximum height. So to find the maximum height, look at this expression for, let me call this expression as 2. So now we have to integrate 2. We have to integrate 2 and use the initial condition that v is equal to 0, v is equal to u at t equal to 0, and well, when we integrate, we have that z is equal to 0 at t equal to 0. So we use this particular initial condition to find the expression for z as a function of t. When we do that, I get the following: z comes out to be 1 over k times u minus v minus g over k square times log g plus ku divided by g plus kv, right? And we see that that is, if we want to find the maximum height, we set this v equal to 0. We set this v equal to 0, and that is when we find the maximum height, the z max, right? And that's it. Let me do a quick example. I think, what have we got here? Yeah, we can do a quick example to wrap up this discussion. So suppose the ball, we were doing that resisting medium example. So suppose the ball in the resisting medium. So example number 6. So suppose in example 5, we have the ball is released in castor oil. Is released in castor oil. The same example. Then the question is how long it takes to achieve 99% of its terminal speed, right? Terminal speed. That is the problem. It says, notice that the expression for the velocity has an exponential. So the velocity is never going to die out or never going to reach the terminal velocity, or it reaches the terminal velocity at infinitely long time, right? So practically the particle is never ever going to reach the terminal velocity. So this question says, how long does it take to achieve 99% of its terminal velocity, right? So what do we get? So at the terminal velocity, So the example in 5, the ball example, was being thrown into the medium at t equal to 0. It had an initial velocity u, which was 0, right? So in this expression for this velocity, we will keep u equal to 0 in this castor oil problem. So then we get that v of t comes out to be minus g over k times 1 minus e to the power minus kt, and from here we can find that we have to find that when is this equal to 0.99 times minus g over k, right? 0.99 times its terminal velocity. From here we can solve and find that the time comes out to be roughly equal to k times log 100, right? K times log 100 roughly. For castor oil, when we plug in its values, its material values, value of k, it roughly comes out to be 7 millisecond, right? So that is the end of what we have in terms of the projectile motion in its resisting medium. And in the next module we will try and wrap up this discussion of projectile motion. Especially we will talk about circular motion, and then we will move ahead to the case study of linear oscillations with normal mode, linear oscillatory motion with normal modes. Okay, so thank you very much for listening so far. Thanks a lot.